Okay. So, last couple of the lectures, we were talking about the gas equilation. Yeah. So, we just so the very first thing actually we derived is how does the Gibbs energy of gas phase, pure component, pure gas phase, can be changed depending on its partial pressure, or total pressure, or partial pressure. Yeah. So G of the gas phase is GI naught, pure standard state at 1 atm, plus RT ln partial pressure of I. And partial pressure is mole fraction times total pressure. Yeah. And then after that we actually, I show you actually when you actually mix the two different gas without any consideration of the reaction, when you have the mixing of simply two different gas as one gas solution, there's always entropy, the entropy of mixing, which is positive term, actually generate during the mixing. And that entropy is the driving force for the mixing of the gas phase. So there's no pure gas phase. Whenever you have the gas phase, it always wants to mix it together instead of having separate gas phase, okay, because of the entropy mixing. And then I introduce you, okay, when you consider now some chemical reaction between the gas species, how to actually get the final equilibrium state, okay. And there's the two ways to actually calculate the final equilibrium state. One is to find out the minimum Gibbs energy state by just doing the derivation of the Gibbs energy as a function of the mole fraction or chemical composition of gas phase. And this can be done, this is numerically easily done by using computer code. But if you want to do this kind of the approach by using just calculation by hand, it's very difficult. Manually, it's very difficult. So that's why we introduced the other method, which is just using the equilibrium constant. Okay? So when you have any gas species which is in equilibrium state at the given final equilibrium state, so final state, it means equilibrium state. When you have that equilibrium state, the internal gas reaction to make another gas phase. So for example, CO, oxygen, CO2. Internally, this should have the equilibrium state. Okay? So you can pick up whatever gas reaction inside of that final state, and the final state should be in equilibrium state. And when you have any chemical reaction is in equilibrium state, it means delta G of reaction equal to 0. Then you can eventually derive delta G naught equal to minus RT ln equilibrium constant, K equilibrium constant. Okay? Inside of this K, you typically have the partial pressure of gas phases. Okay? And when it is the pure solid is involved, or pure solid or pure liquid, other than gas phase is involved inside of this kind of chemical reaction, and then if this component, solid or liquid phase, is the pure stoichiometric component, then we can assume that activity of this kind of component equal to 1. So it's not really contributing inside of K equilibrium constant. Okay? So only the gas partial pressure is taken into account inside of this equilibrium reaction, equilibrium calculation. Is okay? That's what we have done. And that's actually and also actually some of the example I show you for the oxidation and reduction calculation, we're talking about all kinds, so especially the last question I show you in the last class, that's actually very important. I love those kinds of questions. Okay? So when I say I love, you actually understand what I mean. So your midterm is coming very soon. I love that type of the question. Okay? So I don't give you any specific, the information about your midterm, but I like it. Those type of questions. Okay, now, today we're going to actually look at this oxidation reduction reaction a little bit more in detail, okay? So especially when you have a metal reacting with oxygen and become a oxide, for example, at given temperature, what would be the minimum partial pressure of oxygen which make that chemical reaction happen? Or what would be the minimum, or what is the maximum partial pressure, or what's the minimum partial pressure to make a reduction of the oxide to the metallic phase? Okay? So we already did this kind of calculation in the question number 1 and question number 2 in the in the homework example, I mean the exercise we did it last week. But let's look at a little bit more actually the systematic approach, how to calculate those kinds of things. And especially so-called Ellingham diagram, more graphical actually the representation as well. Okay, so that's the topic today. So this is chapter 3, 2, is it right? So today the title is so-called Ellingham diagram. Okay? So Ellingham diagram is suggested or presented by the Dr. Ellingham. So we just named after him, Ellingham. And this was 1944. Okay? So what is Ellingham diagram? And this is basically collection of oxidation or reduction reaction of metallic phase. Or oxidation reaction of the metals or reduction reaction of the metallic oxide. Okay? So it's the collection of all these kinds of thermodynamic information, especially collection of reaction of the oxidation and reduction reaction. Okay? So you see a lot of the thermodynamic table. You saw actually some table, thermodynamic table for your homework number 1. And then when you look at actually the most of the thermodynamic book, at the end of the book, there's appendix showing the actually thermodynamic table for the oxidation chemical reaction. So for example, aluminum reacting with oxygen become aluminum oxide. Iron reacting with oxygen become iron oxide. Okay? And the reaction Gibbs energy, delta G naught, is represented delta, the A plus BT terms typically. As you did actually, barium oxygen become barium oxide. Okay? So basically, Ellingham diagram, so this is diagram, so this is temperature, okay? Whenever you have the chemical reaction, you can plot the delta G naught of reaction. So for example, so let's assume this is A plus O2 become AO2. At least O is gas phase. A and AO2 could be solid or liquid phase, depending on the temperature. But there's always oxygen involved. Okay? So, when you have this kind of chemical reaction, A plus O2 become AO2. So this is gas phase. And we can define what is delta G naught of this reaction. And this is basically Gibbs energy of AO2 minus Gibbs energy of A, Gibbs energy of O2, yeah? And then this is pure standard state, like this, okay? So this one. And this is typically A plus BT. So it's almost linear function with the temperature, okay? That's actually this graph here. So delta G naught of reaction, delta G naught of reaction with the temperature, okay? And it's not only one, actually the Ellingham collected all the metals which is available at the time. So we have about 25 different kinds of metallic species. And then when you actually make a reaction with oxygen, and it make metallic oxide. And that collection of the different graph is so-called Ellingham diagram. Okay, the collection of the different oxidation line, that's the Ellingham diagram. Okay? So Ellingham diagram, a lot of people say, okay, this diagram tell you, okay, whether your metallic phase become oxide or oxide phase become reduced to the actual metallic phase. But when I actually, from my point of view, this is thermodynamic table. So instead of having the tables, you have only one picture, one graph, which have collection of A, O2, and then there's the, for example, B, plus O2 equal to BO2 and etc. So you have all this one into the one graph. So basically, even though you don't have the real delta G naught of reaction as a function of temperature indication, but when you have this kind of graph, you can actually find out what's the delta G naught of reaction. So for example, when I have this kind of chemical reaction, if I want to actually calculate equivalent partial pressure of oxygen, then I need delta G naught of this reaction, because delta G of reaction equal to delta G naught plus RT ln, and delta G naught plus RT ln K, and delta G becomes 0. That's the equilibrium state. And so I need delta G naught at the given temperature. For example, if I read this one, this is my delta G naught for this A plus O2 become AO2 chemical reaction. Is okay? So it's a collection of the thermodynamic data, oxidation reaction of the old metals into the one graph. That's the Ellingham diagram. Okay? Good. Then let's look at it inside the Ellingham diagram. Then, is it just simply collecting the Gibbs energy like this? No, that would be too simple. So there's nothing he can actually claim the value of this kind of diagram. Yeah? So he actually, very creatively, he actually find a way to calculate the partial pressure of oxygen, equivalent partial pressure of oxygen, to make this reaction in balance. So according to the equivalent, so for example, now let's look at this one. The real value of this graph is like this. So when you have A plus O2 become AO2 gas phase. And equivalent state, it means let's assume we have delta G naught of this reaction. Okay. And equivalent state, that means when A become AO2 or AO2 become A, same. So we are moving both forward reaction or backward reaction. That's equivalent state. So then at equivalent state, we have A metal is almost going to make A oxide, and also A oxide is almost reduced to the metal. That's the equivalent state. So in terms of, for example, this is PO2. So this is A and this is AO2. So if my real equilibrium, so this is PO2 at equilibrium state. So when I have the PO2 equilibrium state at this point, so it means A and AO2 can exist together. Okay? So this value is very important. Equilibrium value of the oxygen is very important, because now if you know the theoretical value like this, and if I put my A into this partial pressure here, so above than this one, then A will be A oxide, yeah? And if I put the A oxide into this partial pressure, which is lower than equilibrium partial pressure for the A and A oxide reaction, then my A oxide will reduce back to the A metals. So this value is very important industrially. Okay? Very important for the many, many different kinds of industrial application. Okay? So mathematically, we can actually derive this one in this way. So mathematically, at equivalent state, delta G of reaction equal to delta G naught of reaction plus RT ln partial pressure of O2. So this will be, and then at equivalent state, this is 0, okay, and this equal to 1, and this equal to 1, okay. Then eventually this is delta G naught of reaction equal to RT ln PO2 equilibrium. So I say it's equilibrium state. Is okay? So mathematically we can do this calculation like this. If we know the delta G naught of reaction value directly. Okay? So if this is A plus BT, we can enter that T at the given temperature, then we can calculate what's the partial pressure of oxygen for that specific condition. So this is partial pressure which can, at that given temperature, which under this partial pressure, your A and AO can exist together. It's not really oxidizing, or it's not really reducing. It's really both A and AO can exist together. That's what it means, yeah? And then, if you know those kind of theoretical value, and if you know that, then based on, and then if you compare that with the real process value, real PO2, real partial pressure oxygen in the system, you can tell whether the A become oxide or A oxide reduced back to the A metal. Okay? That's the one of the way. Okay? Good? So that's why PO2, equilibrium PO2 is very important. Okay, so mathematically we can calculate in this way, but what Ellingham did is he actually represent this one in graph in his diagram. Okay, how he did it is like this. Okay, so here that, so let's assume this chemical reaction A plus O2, AO2, this is gas phase. And this is delta G of reaction. So this is delta G reaction graph with the temperature. So this is delta G of reaction graph. So y-axis, delta G of reaction, and x-axis is temperature, because delta G of reaction, typically delta H of reaction minus T, delta S of reaction, and this is almost A plus BT. So A corresponding to this one, and the B corresponding to the minus S here. Okay? So most of the case, if there's no phase transformation, so A is solid A, like FCCA, for example, and oxygen is oxygen gas, and AO is certain solid AO, then within actually the temperature range for there's no chemical reaction, then this delta H and delta S is almost constant. Okay, so you can actually represent delta G of reaction as A plus BT function. Okay, of course, if you really look at very, very precisely, because there's always a heat capacity which is changed with the temperature, so there's small difference from the linear, actually the graph, but more or less delta G of reaction, if there's no phase transformation involved, that actually become more or less A plus BT. Okay? So that's this linear graph. Okay? And then, okay, so according to the equilibrium reaction, so this one. So according to the equilibrium calculation, you have this delta G not equal to RT ln PO2, yeah? So what he did is like this. Okay, that's good. Let's take, so this temperature at 0 Kelvin here, 0 Kelvin. Okay, I want to just put this graph into this graph here. So this is delta G of reaction graph, and then he just say, okay, how about I just set from 0 here, and then I draw the line, and this line is function of R ln PO2 and T. So basically I just modify this one, R ln PO2 times T. This is function of temperature, linear graph. This is linear graph, and absolute value when it's 0 Kelvin, delta G, the y-axis will be 0. Okay, y equal to AT type of the graph here. Okay, so when I draw this kind of graph, okay, so I want to calculate, so basically this is the idea. Okay, so let's assume mathematically, if I want to calculate at this T1 temperature, I know this delta G not of reaction, so I can enter this one here, I can calculate PO2. That's mathematical way. Okay, instead of that, graphical way, if I have this one, this graph, delta G of reaction here, okay, I just plot it in this diagram. Then I plot the second diagram, second line, delta G equal to R ln partial pressure diagram. This meet together, so when this one equal to this value, so this value, and T equal to this one. And to get this one, I need a certain PO2 from this graph. And along this graph here, PO2 is always same. Yeah? PO2 is always same. Okay? And then what it did is, okay, so it tries to calculate all these different PO2. Okay, so when this slope, basically slope is R ln PO2. So to get this slope, what will be my partial pressure O2? To get this slope, what will be my another partial pressure O2? And etc. and etc. And then instead of doing the mathematical calculation, because I know this partial pressure is PO2 equal to, for example, 10 to the minus 10, this PO2 equals to 10 to the minus 20. Okay? Then I can get this graph and I can get this graph. Then instead of doing the mathematical calculation, basically, okay, if I have this chemical reaction, A plus oxygen become AO2, and if I know the temperature, just draw the actual linear line, and then that slope here corresponding 10 to the minus 10, then okay, the equivalent partial pressure to make A plus O2 become AO2 at this temperature should be 10 to the minus 10. This is 10 to the minus 20 at this temperature, 10 to the minus 30 at this temperature, and etc. Is it okay? Do you get it? So you are doing mathematical calculation one by one. Instead of doing one by one mathematical calculation, Ellingham just plot all this line inside of graph. So you don't have to do any further calculation. You just read this one. Okay, this slope is 10 to the minus 10. So whenever actually you have chemical reaction at this one, equilibrium partial pressure for A plus AO, A plus O2 become AO2. The equilibrium partial pressure is corresponding to this partial pressure from this graph. That's the slope of this graph. So you have two equations. This is original delta G of reaction for each oxide, metal to the oxide. And then we draw another graph here, which just showed actually the linear graph with the temperature, but the slope of this graph is different partial pressure of oxygen. Okay? And then now, I mean, this is okay. I mean, whatever you do, you can get it. But now, let's look at it in this way. So basically, he explained this concept, but all different methods. Of course, this should be Kelvin, theoretically. And then this is 0 Kelvin. And this is 0, value 0. And this delta G naught of reaction. Let's assume this is A plus O2, AO2. C is confusing. D plus O2, DO2. So other oxide. Okay? When you draw one line here, yeah, 1 atm, or partial pressure. Partial pressure equal to, partial pressure can be less than 1. Yeah? Could be higher than 1 too. Yeah. Yeah, typically less than 1. Yeah, you can go if you like. If you go this way, yeah. But most of the time we actually less than 1 atm. Yeah. So this is the real idea. Okay, so when you have the 1, I mean this is simple. But now let's look at this. And this graph, for example, if I draw this one, okay, this graph is corresponding to PO2 equal to 10 to the minus 10 atm, for example. Okay? Then what is interesting is, for the chemical reaction, for A plus O2 become AO2 at this temperature, and chemical reaction for B plus O2 at the PO2 at this temperature, and the C plus or T plus O2 at this temperature. All these three have exactly same answer for the partial pressure of oxygen, equivalent partial pressure of oxygen. For this one, 10 to the minus 10. To make this one equilibrium at this temperature, it's 10 to the minus 10. And this is also 10 to the minus 10. Do you see what I mean? Is it okay? Do you follow me? So if you have, mathematically, if I have this equation from this graph, I can read this graph and I can find what's the delta G naught at given temperature. I can simply do the equilibrium calculation like this, yeah? I can get the partial pressure of oxygen, okay? Same thing for the second graph and third graph, one by one, okay? But if you actually look at this line here, is basically representing delta G equal to minus RT, R ln PO2 times T. Regardless of your chemical reaction, whatever you do, this one is representing R ln times T. So along this line, any chemical reaction, interfering with this line, at that intersection point, the partial pressure of oxygen should be all same. Because this is one partial pressure line. All this one is one partial pressure line. Temperature can be changed. Okay? So for this delta G naught with this one, the partial pressure 10 to the minus 10. For this, at this temperature, if you enter it, the partial pressure 10 to the minus 10 and etc. Okay? So Ellingham proposed the way to read what will be the partial pressure of oxygen for any metallic oxidation or reduction reaction, equivalent actually the partial pressure of oxygen for the oxidation reaction or reduction reaction in graphical form. So instead of doing mathematical calculation, you can actually get it directly from the graph. So what he did is like this. He have all this diagram, and then he just put the scale bar here along this way. Okay, so this is 10 to the minus 10, 10 to the minus 8, and this is 10 to the minus 15, 10 to the minus 20, 10 to the minus 30, and etc. So basically, okay, good. Now, if I have this graph, because this is basically slope along this line, partial pressure of oxygen slope along this line, same thing. This is partial pressure of O2 slope along this line. Okay? So, if I have this one, okay, in the 1944, you didn't have a calculator. So think about it in this way. 1944, you didn't have a calculator. So, how many people know the logarithm? You have to calculate logarithm here, yeah? So, if you have much better table, it will be much easier for the people actually say, okay, you have problem now here, and you don't have problem here, yeah? So that's basically the map for the engineer at the time. So, okay, so I have B metal in my furnace. Okay, my furnace temperature is 1000 Kelvin. Okay, so what will be the partial pressure of oxygen I have to control to make sure that my B metal cannot be B oxide. So I have to maintain below certain partial pressure, yeah, to maintain the B as a B metal. Then I have to know what's the maximum, the equilibrium partial pressure to make a B become B oxide, yeah. So if I maintain below that partial pressure, I'm okay. Okay, so instead of doing the mathematical calculation, you bring this map, okay, and say, okay, I have ruler, so I draw the line from here, goes through this one straight, and make a straight line. Okay, 10 to the minus 30. So if you are 10 to the minus 30 or below, you don't have an oxidation problem. It's kind of the calculator at the time. Partial pressure of oxygen calculator, equivalent partial pressure of oxygen calculator. Everything is written just on the side. The answer is there already. You don't have to do any mathematical calculation. That was the idea. It's a good idea, yeah? Okay? Even think about it. Even now, if you don't have any calculator, if you have the just delta G of reaction with a certain value, can you calculate really partial pressure of oxygen accurately? No, it's not that easy because it's logarithm term. Okay, but if you are using this graph, you need just the ruler, and then just draw the straight line. Even you don't need the ruler. Whatever actually the way you can actually draw the straight line, you can get equilibrium partial pressure of oxygen value directly. That was real idea behind of this Ellingham diagram. So it's a graphical representation of oxidation reduction reaction, and then inside of this graph, inside this diagram, you can get what is the partial pressure of oxygen value to make chemical equilibration between the metal and the metal oxide. Okay? So, even now, in this day, if you actually go to the industry, people still using the Ellingham diagram. So they have only this, the very old engineer, they just still have this big chart of this one and take this one. And then when you go to the, plant and people say blah, 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 and as a senior researcher, which have 30 years of experience in this field, this should be not good. This is okay. You have to change this one. This is the still actually going on. Okay? That's Ellingham diagram. Okay, but that's actually a very interesting thing. Okay, now let's look a little bit more in detail, more inside of the Ellingham diagram. So this is the basic idea. So Ellingham diagram is the collection of the delta G of reaction for the metal become metal oxide. Okay, but one assumption here is, because this is delta G not of reaction, so standard enthalpy of reaction, we assume all the solid metal, or all the oxide is pure stoichiometric compound. There's no solution for the solid solution or liquid solution. Everything is pure solid or pure liquid. Okay, the only thing change is the partial pressure of oxygen. Okay, that's the one of the weakness, because in the end, when you actually go to the real plant, the industrial scale, most of the matter is not pure anymore. So we have to consider interaction between the one element to the other element as inside of solution. But anyway, nevertheless, if you just consider this is almost pure material, you can still use this one to judge what's the partial pressure of oxygen. Okay, now, because this is the collection of thermodynamic table, there's a lot of information you can actually take it out from this diagram. So let's look at another one again. Now, let's consider this one. So all this, when I actually write all this one, I always write 1 mole of oxygen. This is very important, 1 mole of oxygen, because if you want to use this kind of graph, this is the PO2 1, yeah, times power 1. So it means you need 1 mole of oxygen. Or if you want to do it, everything should be half mole of oxygen. So all this chemical reaction you are actually plotting in the Ellingham diagram should have exactly same amount of oxygen. Either 1 mole or half mole or 2 moles if you like. But everything should be based on the exactly same number of moles of oxygen. Otherwise, graph cannot be actually compared with each other. The chemical reaction cannot be compared with with the different amount of oxygen. So for example, if you make twice of this chemical reaction, delta G of reaction become twice bigger or twice more negative, yeah? So if this is negative value, so 1 mole of O2 is like this, and 2 moles of O2 means 2 moles of A, 2 moles of O2 become 2 moles of AO2, then delta G curve will be here, yeah? But that actually containing 2 moles of oxygen, so it cannot be in the same line, according to this actually the calibration of oxygen line. Okay? Oxygen equilibration line. Okay? So Ellingham diagram, the idea is collecting all this thermodynamic Gibbs energy of reaction, but all this one is based on 1 mole of oxygen. So this is baseline. So this is baseline assumption. 1 mole of oxygen all the time. Okay? And then Now, let's look at it in this way. Okay, so I have one curve, the other curve. So, for example, when this is A plus O2 become AO2. Let's assume this is solid, and this is solid, and this is gas phase. And then A could melt at certain point here. There will be A melting temperature and A boiling temperature at certain point too. So typically in the Ellingham diagram, we have to collect all the thermodynamic information. So when you say M, and then typically means A become liquid phase, O2 become AO2, solid. And then this is, for example, L or M melting and solid. Vapor V or B, depending on the case by case, B, it means boiling temperature. So it means above this one, typically A gas phase. That's what it means. So we have indication of the phase transformation. When you change the phase transformation, we are changing the slope. Okay? So let's look back again. So this is, for example, A plus BT curve in the Ellingham diagram. Okay? And this A plus BT is theoretically delta H of reaction minus T delta S of reaction. Pure material. Okay? So why then most of this graph I draw so far is upward actually slope with the temperature? Why is positive slope with the temperature? I haven't drawn anything with the negative slope so far for the chemical reaction. Yeah? Why it should be positive slope? Because A is solid, AO is solid, O2 is gas phase. Entropy of the any kind of species with the gas state is much, much bigger than entropy of solid or liquid state. Yeah? Am I right? So reactant entropy is much bigger than product entropy. Okay, so delta S should be negative. Am I right? Delta S of the product minus S of reactant, because reactant have much positive entropy because it involves oxygen, gas phase. And solid, and this is gas phase. Gas have much bigger entropy, so reactant have the bigger entropy. So delta G of reaction, delta S of reaction is negative term. So negative, negative is positive term. So that's why slope B here will give you the minus delta S of entropy, and this is mostly positive. Okay? And then when it becomes liquid phase, it becomes a little bit more positive because solid become liquid. Liquid have a little bit higher entropy than solid. Am I right? And then when it becomes gas phase, A becomes gas phase, it's much bigger difference now. The slope change here is actually very huge. So this is much marginal and this is much bigger because now 2 moles of gas phase in the reactant. So the entropy is twice bigger than the solid state. Okay? So typically this slope, which is minus entropy of mixing, minus entropy of reaction, which become more and more steeper when you actually change with the increasing of temperature, because your reactant have the more entropy. Okay? You good? Evaporation of the oxide is need very, very high temperature. So most of temperature range, we don't see the evaporation of the oxide. Okay? So when you typically see this kind of M and the B, so this means, okay, melting temperature of the reactant metal and the boiling temperature of reactant metals. Okay? So you know the even temperature of the melting of A and the boiling temperature of A as well in the one diagram. Okay? Of course, now if you actually extrapolate this one down to the 0 degree Kelvin, then you can calculate delta H of reaction, delta G naught of reaction, delta H naught of reaction. Yeah? Okay? You good? Or if it is at 298 Kelvin, if it is at 298 Kelvin, A solid, H 298 of A solid is 0. That's a typical reference state for A solid. Oxygen, reference state 2 at 298 Kelvin, O2 gas phase. So this value here, when you know what's the delta H of reaction, that should be corresponding to the H, delta H of A, standard entropy of formation for the AO2 at 298 Kelvin. Yeah? Because you know the slope, so from delta G, you can calculate what's the delta H of this one at 298 Kelvin. Yeah? Okay? There's a lot of information, a lot of thermodynamic information involved inside here in the one graph. Of course, also there's chance for the oxide become liquid phase too. Yeah. So when we have typically that happen, so for example, let's assume this T not like this. This is too much. So when this is A, for example, liquid, you can have this case too, yeah? Then we put it like this. So we have different symbol. I mean, it's depending on the version by version, but typically, at least we are representing metallic melting and oxide melting as a different symbol. Okay, so in this case, so if I have the M inside of circle, this is, for example, oxide melting temperature. So melting of oxide. So that's why slope is slightly become negative, yeah? Slightly become smaller than the previous one because entropy of liquid phase in the product side, entropy in the product side is going up. Is it okay? But the slope change is very small typically. Okay, so this is the melting temperature of AO2. Yep, this temperature here. Okay, good? If you look at Ellingham diagram, there's the only one species which have typically negative slope. There's actually one which have, I mean, delta G of reaction is negative. And that one is this one, carbon solid reacting with oxygen, 1 mole of oxygen become 2 moles of CO gas phase. This should be negative. Because entropy of the reactant side have the only 1 mole of gas phase and the product side have 2 moles of gas phase. So the entropy of the product is bigger than entropy of reactant in this case. Is it okay? So it have negative slope. This is one of the only one you can see it in the Ellingham diagram which have negative slope with the temperature. And there's actually one also have almost zero slope. And that is C plus O2 so one solid, gas phase, gas phase. So reactant have 1 mole of oxygen, product have 1 mole of CO2. So it's gas. Solid is very small. So the slope is, entropy is almost equivalent. Okay? Because this is very small. Entropy, from the entropy point, this is very small. This is very big. This is same as, almost same as this one. So these two is balanced together. It's become almost zero. Okay? And you know, carbon or CO2 gas is typically used for the reduction of the metallic or the oxide to the metal. So blast furnace in steel making, in the iron making, so iron oxide is reduced by the CO gas to make a iron metal phase. Yeah? Okay? So now let's look at this way. And then actually now if you look at the Ellingham diagram, okay. So we could have, for example, the most famous one, AG solid or liquid, it doesn't matter. So AG, so silver, AG. As you know, AG is the very noble metal, yeah? Noble means it's not reacting very much with oxygen, become oxide. So when you have silver is always like shiny. Wow, you can make a lot of scratch, but it's that actually because of reflection problem, but typically when you do the polishing of the silver, it's very shiny. It doesn't have the oxidation reaction that much. Okay? Because if you look at actually AG in this diagram here, so your zero line is somewhere here. So as I mentioned, as one of you mentioned, okay, so up here probably PO2 equal to 1 atm. So when you have PO2, so below the certain temperature, you could have oxidation reaction because at air condition, you actually touch this line in some cases. Okay? But because the temperature is too low, so the kinetic of oxidation is very, very slow, so there's no oxide formation. But now if I want to actually make this chemical reaction happen more quickly, I want to increase temperature. But when you increase temperature, your PO2, 0.21 is here, and so it's actually all this reaction occurring above than even 1 atm of oxygen. So typically, silver cannot be oxidized under normal condition. Silver is one of the top one in the Ellingham diagram. Okay? And then some of the actually famous one you know is I have, for example, FeO. Because it's 1 mole of oxygen base. Okay, chromium, and then you could have something like this. You could find all this kind of thing. Okay, there's tens of them, but some of the most common one you can see in the material science is this kind of thing. Okay, so that means, so if you just look at it in this way, so let's assume at the same temperature, okay, at the same temperature, if I draw what will be the equilibrium partial pressure to make this metal become oxide in equilibrium state. So reduction, reaction, oxidation, reduction, reaction, equilibrium partial pressure of oxidation, reduction, reaction. So this will be higher than this one. this will be higher than this one, this will be higher than this one, this will be higher than this one. So this one, the very bottom in the actual Ellingham diagram, have lowest partial pressure of the equilibrium to make oxidant reduction reaction. Is it okay? Do you get it? So let me rephrase it again. So because this one at this temperature, for example, 10 to the minus 30 PO2 to make this equilibration, calcium become calcium oxide. And this one 10 to the minus 20. And this one 10 to the minus 10. Okay? I mean, according to our previous line, we show you, it should be like this way, yeah? So it means whenever, so any, actually the metal, which is the lower side or bottom of the Ellingham diagram, so it means delta G naught of reaction is negative, more negative, you have more chance to become oxide. Because even under the very low partial pressure of oxygen, it can become oxide, yeah? Okay? So this one requires 10 to the minus 10 ATM to make a FeO. Fe become FeO at 10 to the minus 10. This calcium become calcium oxide at 10 to the minus 30 ATM of oxygen. So it means anything in the bottom of this graph become more stable as oxide form. Anything in this diagram which exists in the higher position is more stable as a metallic form. Okay? Do you get it? So anything you can think about very reactive metals is always in the bottom in the Ellingham diagram. Anything which is very noble is stay on the top of this diagram. Okay? You good? Now this is very interesting story because when you produce, for example, iron to the iron, so iron oxide to the iron, okay, you can react this one with this one. So I mean this is stupid because calcium is more expensive, but if you mix the iron oxide with the calcium oxide will be formed and reduced iron to the iron metal. Because anything at the given temperature, any metallic element in the bottom of the Ellingham diagram is more stable as oxide than above, anything above actually each line. So it means if I mix FeO with calcium want to take this oxygen, want to become calcium oxide. And while doing that, this one become iron metal. Okay? And this is conceptually. And mathematically, of course, too. So for example, let's assume this is delta G naught 1 reaction, delta G naught 2 reaction at the same temperature. So when you have 2 Fe plus O2 equal to 2 FeO, this is delta G naught 1 and 2 calcium okay. Then this will be 2 calcium plus 2 FeO equal to 2 calcium oxide plus 2 Fe, and delta G of this reaction is delta G naught of this reaction is delta G naught 2 minus delta G naught 1. Okay? Is okay? And delta G of reaction equal to delta G naught of reaction plus RT ln partial pressure or activities is 1, yeah? There's no partial pressure involved now. Everything is solid or liquid, pure stoichiometric phase. If you assume the calcium and the iron is not mixing each other, or iron oxide and calcium oxide is not mixing each other, everything is insoluble, stay as a separate phase, then inside here is everything is 1. One scale, yeah? So activity is all 1. So this is 0. Basically this is same as this one. Okay, so is delta G of reaction is negative or positive? That's depending directly delta G naught of reaction. Yeah, that tell you whether the chemical reaction going to the forward or backward. Okay, so direction. Is this one going to the forward reaction or backward reaction? Yeah, forward, because this is negative and this is less negative. So for example, this is minus 1000, this is minus 500. Then it becomes minus 500. Yeah, so which is negative term. So this is negative, so delta G of reaction is negative. So this is less than 0, so it means the reaction going to the forward. Calcium metal can be used for the reduction of iron oxide to the iron metal. Is it okay? Is it good? Anything in the bottom of this Ellingham diagram, any metallic element in the bottom of this diagram can be mixed with, can be used as a reductant of the oxide in the above Ellingham diagram here. The oxide in the above actual side of this diagram to make a metallic phase. Okay? But naturally, calcium oxide, if you look at it, naturally, calcium will be in form of calcium oxide, yeah? So you have to produce calcium metal from calcium oxide first to do that process. And this is more expensive than this one. There's no stupid guy who will do this way. But theoretically, if you want to do it, you can do it. You okay? You good? Now, this is the reason actually we are using this one, carbon, very cheap one. So carbon, the main source of carbon is coming from the coal. Coal. Coal is very cheap compared to the metal. Okay? So that's why, another case, so you have now this COO2, so this one, CO, so this chemical reaction, so I'm sorry, there was mistake here, yeah, 2C. Yeah. Okay, this one. And then if you have now this one. Okay, so if you look at this one, at this temperature here, this one, so if I want to now make this one, FeO, if you like, this way. So I'm mixing this one and this one. This minus this one. Okay? And this side here. So this minus this one. This is positive, yeah? So this chemical reaction here. So let's assume this is delta G of reaction Fe or redox reaction 1. So at this one, delta G of reaction 1 is positive. And this side, negative, yeah? So I'll examine. Okay? This minus this energy, so this minus this energy, that's a delta G naught of reaction 1. So positive and negative. So it means above this line, according to the Ellingham diagram, if you have the iron oxide, FeO, if you mix that with carbon, it will produce iron metal and the CO gas at above this one. So chemically, above this temperature, you can reduce iron oxide by using the carbon to produce the iron metal. And the product is the CO gas. Is it okay? That's about 800 Kelvin. Okay. So, and also interestingly, this graph is only negative slope. So all this MO, chromium, and all this one actually almost touching this line eventually. So if you look at here, all touching this one. So this is carbon. So iron, sorry, the iron. So this one touching very low temperature, about 800 degree Kelvin. This one here touching about 2,500 degree Celsius. So it's too high. So that's why we cannot reduce the CaO by the carbon easily. Okay? It's industrially, theoretically it's possible, but industrially it's very difficult. Okay? At that condition, calcium is also gas phase already. Is it okay? And then, so this is good. So coal, we can use it. But one of the very interesting addition inside of Ellingham diagram is, okay, so we want to, so from the diagram we can understand now what is equilibrium partial pressure of oxygen to control, to make a reduction and the oxidation happen, okay? But most of the industrial process, we are controlling the partial pressure of oxygen by using the CO-CO2 mixture or H2-H2O mixture, okay? So let's assume in the 1944, okay, I know the PO2, but now the actual customer will say, okay, so the engineer say, okay, your PO2 is too high. You should control it 10 to the minus 20, and you are 10 to the minus 10, so it's too high. You have to reduce it down to the below the 10 to the minus 20. Then the client will say, okay, so how can I do it? You have to reduce 10 to the minus 20. So how can I do it? And so engineer have to say, okay, you can mix the your CO2 together to control that. Okay, so what's the CO2 value? I have to go calculate it. That's wrong, yeah? You have to give the answer directly. So H2 ratio should be this one. Or CO2 ratio you have to inlet should be this one. Ellingham actually put the that value inside of the diagram too. It's smart, yeah? So here, I believe it's very smart. Okay, so how he did it? So, okay, so this was the question. And he basically did it in this way. Okay, so in the Ellingham diagram, so this is T. Let's assume this is A plus O2 become AO2 again. Delta G naught of reaction. Okay, that, I mean the zero, this was the partial pressure of O2 line. Starting over the partial pressure of O2 line. And then we read the PO2 here, yeah? Okay, that was smart. And then now he actually introduced the other one. Okay. So according to this diagram, actually you can even draw here H2 you can draw this diagram, this line too, yeah? I mean inside, this is also oxidation reaction between gas oxidation reaction, yeah? H2 gas reacting with oxygen become H2O gas. Okay, but how can I actually then, so the question is, okay, at this temperature, I draw this diagram, I know what is PO2 here from this diagram. Is there any way I can calculate to control this PO2? What would be the H2 ratio? What would be the depth value? Okay. So mathematically, let's look at it. So mathematically, if you want to know this partial pressure, so we have to combine the two equations together. Okay, so 2A plus O2. Okay, so I know this delta G naught of reaction 1. Okay, from the graph. Okay, and then H2 this one. If you want to do it mathematically, you just say, okay, minus of this one, so it will be A plus 2H2O equal to AO2 plus 2H2. And this one is delta G naught 1 minus delta G naught 2. Is it okay? At equilibrium condition, for this chemical reaction is balanced, then delta G of reaction okay, square, I put it in front here, 2. Okay, this value here, so at equilibrium condition this is 0, then this delta G naught 1, yeah, delta G naught 1 minus delta G naught 2 equal to 2R ln pH2O pH2T. Is it okay? So if I know this, if I have given temperature, if I know these two values from the thermodynamic table or graph, I can calculate what is this partial pressure. Yeah. 1 minus 2, 1 minus 2. Yeah. I just changed this one. Yeah. Yeah, okay? Still okay? So I just swap this one to compensate minus. Okay? So, okay, that's interesting. But previously, when you actually draw this graph, I mean, in order to know this point here, I need delta G naught 1 as a function of delta G naught 1 with the H2H2O ratio. Yeah? So mathematically, okay, if I know these two values, so basically this value here at this temperature, this is delta G naught 2, this is delta G naught 1. Yeah? So this is 1, this is 2. So if I know these two values, I enter this one here, and with the temperature, I calculate what's the ratio of these two. Yeah? Is it okay? Mathematically, we can do it. Now, is there any way I can represent this one in this graph, like this way? Can I make some scale to show the H2H2 ratio here? That was the question. Okay, so let's just change this form. Little bit different way. So, okay, so this one. So, delta G naught 1 equal to, I'm moving delta G naught to the other side, 2R ln okay. Delta G naught 2 is, so reaction delta H naught 2 minus delta H T delta S naught 2. Okay, and this A plus BT, this is almost A plus BT term, almost linear with the temperature. Okay, so okay, that's good. This is temperature dependence, this is constant plus temperature dependence term. Let's collect temperature dependence term together. minus this delta T plus okay. Okay, so this one, this is slope here. It's constant value. Yeah? So I enter the constant value there. And so somehow I have to calculate this one. At each line, I have slope with the temperature. So delta G1. So this is delta G1 graph here. This is delta G1 graph. And all the delta G2 information, G02 information can be just transformed to the two constant value inside of this equation. And then, if I draw this line, somehow through this point again, and if I make this point here as, instead of 0 now, delta H2. When t equal to 0, this is 0. Delta G not 1 is same as delta H not 2. So if I put the delta H not 2 here, sorry, this is not very good. According to this graph, it should be here. So this one. Because this diagram here, delta G naught 2, this diagram is delta H naught 2 minus T delta S naught 2 at 0 degree Kelvin. This is same as delta H naught 2. Okay? So this one. And so this is H2, H2O reaction point, starting point at 0 Kelvin. So if I take this point, if I draw the straight line now to this delta G naught 1, the slope here is 2R ln pH2O or pH2 minus delta S naught 1. And this is constant, so I can draw each of this slope and then define what will be this value. Okay? So basically, according to that, he just say, okay, here, so pH2, pH2O, actually, he typically represents in this H2, H2O, H2O, H2, doesn't matter. So this is 10 to the 3, 10 to the 2, 10 to the 1, 10 to the minus 5, and etc. Okay? So, this diagram now tells you two information. One, make sure that A become A oxide and equilibrium state. What will be my partial pressure of oxygen? I draw it from 0 point here, straight line, and then read this PO2. That will give you partial pressure of oxygen. Okay? In order to get that partial pressure of oxygen, what would be my H2-H2O ratio? Read from here, H2-H2O actually starting point, draw the straight line through this point again, and then, okay, 10 to the 3. Okay? It's graphical representation of the answer of all this one. And, okay, so H2-H2O we can do it. How about CO, CO2? We can do the same thing. So, we have another one. CO, CO2, same kind of idea. And then now you can draw it same way. And then here have the graph, scale on the side of this graph, CO, CO2 as well. That's the whole thing of the Ellingham diagram. Okay? So Ellingham diagram is practically very, very useful, especially for the field engineer who don't have the calculator. They can directly tell, okay, how to control the partial pressure of oxygen, what's the control value for the partial pressure of oxygen, and how to control that by using CO, CO2, and H2, H2O. Okay? And also, when you produce some metal, what kinds of the reductant I can add in the furnace to reduce those oxides to the metal, according to this balance. All those information is inside of one diagram. Okay? We good? So we'll practice how to really use this Ellingham diagram next class. Okay? And that's basically all the content you have to prepare for your midterm. Okay? Okay, any question? No? Okay, see you on Wednesday then.